Okay, good morning, good afternoon, and good evening to everyone, wherever you are in the world. My name is Orad Reshef, and welcome to this third edition of the flagship Photonics Online Meetup. We are very excited to have you today and to show you guys our lineup and what we've been working on. I guess I'm not going to waste a lot of time. I just want to thank the generous support from Photonics Media, from the CRPUO, which is the Center for Research in Photonics at the University of Ottawa, JCEP, which is the Joint Center for Extreme Photonics, and the USC School of Engineering. These four organizations have combined to foot the bill for this entire conference out of pocket, so that everything you see here, from the poster session to the booths in the career fair, is absolutely free to everyone participating. You can learn more about these organizations at photonics.com, photonics.uottawa.ca, or at extremephotonics.com, respectively. And without further ado, I would like to introduce the chair for our hot topic session, Mera Kaglayan. Mera, please take it away.
Hey. Hello, everyone. Hello, everyone. Welcome to the hot topic session. I'm Humaira, and I will be chairing this session today. And we are so excited to have you all today. So we're gonna start with Hannah today. And yes, Hannah. So please go ahead.
Perfect. Hi all, and thank you for listening to my Hot Topics talk on a hybrid nanoplasmonic porous biomaterial scaffold for liquid biopsy diagnostics using extracellular vesicles. Okay, so extracellular vesicles, or EVs, are nanoscale packages that range from about 30 to 100 nanometers. They are shed by every cell type in the body, and they are abundantly present in all biofluids. They're really important in cell-to-cell communication. However, this communication route can be hijacked by cancer cells, and they then send their own cancerous EVs to form a pre-metastatic niche where secondary metastasis can occur. Luckily for us, they're also very abundant in potential biomarkers, which makes them really attractive to study for a liquid biopsy platform. So to study these EVs, we have elected to use Raman spectroscopy, which analyzes inelastically scattered photons. Raman is an attractive tool for us because it is inherently label-free, it's non-destructive, and it can be done in an aqueous solution. However, only about 1 in a million or so photons is actually inelastically scattered, which makes Raman a pretty weak process. So to overcome this issue, we can use surface-enhanced Raman scattering, or SERS, which introduces nanoscale metallic materials that then amplifies this Raman signal and provides a really unique global chemical information that can be found on the surface of these EVs. So here, panel A shows our experimental setup with our inverted confocal microscope and spectrophotometer that collects these inelastically scattered Raman photons after they interact with our sample. So for these experiments, we used a novel SERS substrate that was created by mixing diatoms, which we can see here in the SEM image in panel B, with clusters of silver nanoparticles. These substrates also have a unique filtering ability, which we can see in the side profile. And this means that EVs can filter into the substrate and come into good contact with these silver nanoparticles. So when the EVs are in close proximity to the silver clusters, there's a really large amplification of their Raman signal. And we can then analyze the different types of vibrational bonds that are present. And what we wanted to do is see if we could combine this SERS process in conjunction with our EVs to form a liquid biopsy platform for cancer detection. So one thing that we were interested in investigating was this glycocalyx. So if we look in the upper left here, this is a schematic of that. And the glycocalyx is a thick corona of sugars that surrounds EVs. And we were interested in this because we noticed that a lot of the chemical signatures we were seeing were carbohydrate related. SERS itself is a really distance-dependent phenomenon with a range of about 10 nanometers, and we were curious to see if cleaving off this glycocalyx could potentially expose additional surface groups that are present on the EVs, and then that would maybe change the signal that we were seeing by allowing these other entities to be in the SERS enhancement zone. So we decided to create a cleavage procedure using trypsin, which is an enzyme that cuts at specific amino acids and has been used in previous work in our lab. So in the bottom left, this is a 2D principal component graph that shows clinical samples before they were trypsinized. Here, each axis is a principal component that contains a certain percentage of the total variation that we saw between all of the samples that we analyzed. Each marker additionally is a single Raman spectrum, and the shape and the color correspond to the sample diagnosis that can be seen in the legend. So the most important thing to note here is that the samples were actually able to separate based on their diagnosis, with the endometrioid malignancies, which are here in blue, separating from the ovarian malignancies, which are in red. Additionally, both types of cancer were able to separate from our control samples as well. If we then look to the right, this is the same data as previously mentioned. However, it's additionally plotted with the same samples that underwent trypsinization, and the empty markers are the trypsinized samples. So the green, red, and blue spectra represent the most important peaks that were present in each of the different colored clusters from the graph. And there's a lot going on here, but the biggest takeaway is that we saw more chemical signatures that actually related to proteins and lipids rather than carbohydrates. However, the samples lost a lot of their separation when they were trypsinized. So this indicates that different chemical signatures were indeed revealed when trypsinized. However, that did show that the glycocalyx itself might actually be vital to the study of cancer diagnostics. So future experiments will be focused on investigating the extent of the diagnostic ability of the glycocalyx. Thank you for listening.
Oh, thank you for this very nice presentation. And our next speaker is Filippo.
Hello there.
Hello, Filippo. Please go ahead.
Yep. So hello, everybody. It's a pleasure to be here, and I would like to thank the organizers for this opportunity. Tonight, this morning, depending where you are, I'll show you the research we're doing towards Raman spectroscopy in deep brain regions using a minimal invasive multimode tapered fiber. This is work we are doing at IIT together with collaborators in Italy and all across Europe. So you've just heard a fantastic talk on Raman applications, and I cannot move my slides.
Oh.
Okay, thanks. So Anna gave you a fantastic introduction and a fantastic application of Raman, which is indeed a very powerful technique. There are countless areas in which it can be applied, and there's a very interesting one that is coming up in recent years, and it is the use of a Raman endoscope as guidance during surgery. Imagine you were a surgeon performing a tumor resection, and you need to take out the mass but preserve healthy tissue. To make sure you're doing a good job, what you can do is take a Raman endoscope and look at the tissue around the lesion. And from the spectra, you can understand if there are cancer cells still present in what you've left. And this recent paper have demonstrated that there are quite big differences, for example, in the lipid bands in between healthy tissue. You can see it in the fingerprint region around 1440 inverse centimeters, or in the high wave number region around the 2800 bands. And this is a first indication. There's much more detail, but I'll just stop here. So the way people do this is using fiber bundles. This is because Raman is indeed very weak. And when you shine your laser through a waveguide, you generate a lot of background. To avoid this background coming back to your detector, what you can do is use a central fiber and then collect with other fibers. But these are quite big. So we've been asking ourselves, and can you please change slides again, Mira? Thanks. Can we do the same with a hair thin probe, like a multimode fiber, for example, a tapered optical fiber? So insert into deep brain region and collect the Raman signal with depth resolution. These fibers are interesting, and we've been studying them in recent years. No, sorry, still back, thanks. Because they allow you, by playing with the guided modes, to control the depth at which you are delivering light, exciting fluorescence, has been demonstrated in a optogenetic response, and discriminate the depth from which you are collecting signal. So we are investigating how to apply them in a Raman endoscopy perspective. So next slide, please. Okay, here we go. And we started off using a tapered fiber coated with metal with a small optical window open within the metal. And we implanted it in a fixed brain from a mouse model with a metastasis in one of the two hemispheres. And then we placed the brain and the implant under a custom-made confocal Raman system. And we have been looking at the spectra from the healthy hemisphere and the metastasis. And what you see in the two plots is the blue is the healthy hemisphere. The solid line is an average over 5 insertion. You see each insertion in transparency. The red line is the signal from the metastasis. And taking a look at the lipids band, you see that the healthy tissue has signal around 1440 and in the high wave number lipid bands, but cancer has not. There are other features we are not certain about yet, but it's a promising result, we think, towards future work that will hopefully lead us to do in vivo Raman spectroscopy together with the electrophysiological readout of the peritumoral brain activity to understand what's going on around the metastasis. So here I'm closing with the next slide. And I'd like to thank you all for your very kind attention and to acknowledge all the collaborators. I'll be more than happy to take your questions if you're interested, either at my email or on Twitter. So bye everyone and take care.
Thank you. Thank you, Filippo. So the next speaker is Martin.
Thank you very much for the word. So in the work I will present today, we study theoretically the nonlinear optical properties of quantum cascade laser emitting frequency combs in the terahertz range. So quantum cascade lasers are based on intersubband transitions inside the conduction band of a periodic arrangement of semiconductor quantum wells, where population inversion here between this green and the orange states is driven by an electrical bias. The subband system, shown here in the figure on the right, allows for a large nonlinear coefficients as well as tunable emission frequency, which has enabled mid-infrared and terahertz frequency comb operation. These combs are generated by four-way mixing, schematically shown in the lower right figure, which is a third-order nonlinear process originating from the spatial hole burning inside the laser cavity, as well as from the active medium itself. In addition, radio frequency photons are generated by difference frequency generation, which is a second-order nonlinear process. It is therefore very interesting and indeed necessary to study the nonlinear properties of these devices in order to improve future generation frequency combs. However, such modeling is complicated by the fact that many electron states are involved in the transport as well as the optical response. There is a very strong AC field under the operation of the devices, as well as the fact that the transport time scales are similar to the inverse emission frequencies in the terahertz range. These considerations mean that a time-resolved model is appropriate, since it allows for a non-perturbative treatment of the light-matter interaction. We therefore employ a time-resolved density matrix model, which also fully accounts for the coherent transport in addition to the most relevant scattering mechanisms in these devices. The AC field is modeled by a time-dependent external electric potential, which can be of arbitrary temporal shape. In our case, we let two pulses with varying time delay excite the system, and then we record a nonlinear current response, which in an experiment would be the equivalent to an induced electric field response. By making a 2D Fourier transform along the detection and time delay axis, we obtain the 2D frequency map on the right. This is a technique usually called 2D terahertz spectroscopy. For clarity, we use sync pulses, which are shown in the central figure, which have a flat frequency spectrum. This provides a one-to-one mapping between the nonlinear current and the nonlinear coefficients, which on the left is exemplified by a chi2 plotted as a function of the response frequency and one of the ingoing frequencies. A problem with using sync pulses is that they contain DC frequencies, which allows chi2 processes to occur even for this f1 equal to 0, which makes it difficult to distinguish the chi2 and the chi3 responses in the nonlinear current map. We therefore employ a modified pulse, which has a flat frequency spectrum only in a range around the lasing frequency. This allows for assigning the different peaks in the 2D spectrum different nonlinear orders. This can also be seen directly by sweeping the AC field strength, as peaks change in relative amplitude when the AC field is increased. Peaks with higher intensity for high AC fields have a high nonlinear order and vice versa. So in the figure, we can now identify Chi2, Chi3, and Chi4 signals. We can also identify two main frequency components. This one, which is coming from the laser transition, and this one, which is coming from the extraction transition. So let's see if we can. So finally, we track the marked points in the 2D map for increasing AC field strength, and then we can extract the nonlinear order from their slope plotted on a log-log scale. What we see is that the second order and the third order nonlinear signals occur at the expected frequency coordinates and follow the expected power law. At higher fields, however, the nonlinearity saturates as the electron populations redistribute among the subbands, making it hard to attribute specific nonlinear orders. In addition, the whole 2D map becomes distorted at high AC fields as the populations and coherences are driven far from equilibrium. Since the pulses have flat frequency content, we can easily extract the nonlinear coefficients responsible for some frequency generation and four-way mixing, for example, at the lowest AC field strength. And we find a reasonable agreement with perturbation calculations at low fields. In conclusion, our method allows us to analyze and predict the nonlinear response beyond perturbation theory or power expansion formulations for the strong AC fields, which are typically present under laser operation. This method can also be used experimentally, as we have done in this publication here, although it is currently limited by the available pulse terahertz sources. So with that, I would like to thank the organizers for the opportunity to present our work here, and all of you for your attention.
Thank you very much. And let's go to the next speaker. The next speaker is Jinkan.
Hello, everyone. Thank you for having me to give a talk at the POM. Let's get started. Oops. Sorry, the control is kind of messy, but yeah. In optical tuning, resonator is one of the most common building blocks in an optical circuit. Resonators can be characterized either by photon lifetime or cavity resonant wavelengths, which is dependent on the refractive index and the cavity radius. By tuning these two parameters, one can achieve either the tunable lasers or the tunable filters. So far, resonators are made out of a variety of materials shown here. In our lab, we mainly focus on silicon microtorrid devices. As mentioned earlier, by either tuning the refractive index or radius, one can eventually change the resonant cavity wavelengths. So far, most common tuning methods over these two parameters are the thermal optical tuning or the electrical tuning. Here in our lab, we are trying to develop a new method. Our novelty is to use an organic photo switch called aminoazobenzene or AAZO. So we try to surface functionalize a well-ordered monolayer of AAZO on silicon microtorrid devices. The unique part of this organic photo switch is that the AAZO can flip between two geometries with two different indexes when exposing with blue or mid-IR laser. Here's our fabrication scheme and the surface functionalization of AAZO. What we did is we used two silenes, the CPMS and TCMS. The CPMS is to covalently bond the photosensitive AAZO group, while the TCMS is to bond the control methods group. Here's our testing setup. Basically, we use 410 or 450 nanometer as the pump wavelengths, and the 1300 is the probe wavelengths. Both wavelengths are simultaneously coupled into the device via single waveguide taper fiber. Our quality factor indicated that the device device has a range in a 10 to the 5 or 10 to the 6, while bare silica device shows similar quality factor with less than an order of magnitude difference, showing successful surface functionalization with minimal impact on the device quality. Here are what we have studied for reversible device tuning. So on the left figure, it's a one full recycle for wavelength tuning, starting with 4 10 nanometer induced blue shift, and then followed by CO2 laser induced red shift. The device was stabilized in the dark to quench the total wavelength change. We also repeated these reversible cycle for 3 times with different circulating blue power. One thing also should be noted is that on the right figure, we tested the device and we weighed the device in the air for a period of 6 months. And after that, we tested this same device again and showing similar optical responses. This proved the stability of the optical device with the amino azo coating. Here, we also wanted to study how the surface density of azo affects the device responses. What we did is to study the wavelength change as the function of circulating blue power at various azo ratios. The more azo on the surface, the faster further the responses will be at similar couple power. This can be also strengthened by the fact that the refractive index change out of the cavity follows the similar orders of magnitude by the ellipsometry. We also wanted to study how far we can tune the blue shift. To do this, we optimized the azo method ratio at 1:1, showing around 0.7 FSR free spectral range of the cavity. And the max blue shift are also linearly proportional to the laser power. And the bare silica device show no shift in the control. Lastly, I'd like to thank my advisor, co-authors, lab members, and funding agencies. That's all. Thank you for your kind attention.
Thank you, Daniel, for this nice presentation. And then next, we will continue with Erika. Just
hello.
Just a second. This. And yes, then next speaker is Erika.
Okay.
Thank you.
Okay. Hello, thank you all. Thank you for having me and for this amazing opportunity. I am Erika. I work at the University of Southampton, and my hot topic for today is about cavity-induced bound excitons. So the question we ask ourselves is it possible to use non-perturbative cavity effects to engineer quantum materials property, like creating or manipulating electronic states? Well, waiting for so well, to answer this question, we can focus on a specific simple system, such as a doped quantum well. Because the quantum well is doped, the Fermi energy will lie on the conduction band. And if we think that we can make the quantum well narrow enough, we would have just one single subband in the conduction band and a continuum of ionizing states above the ionization threshold. If one electron jumps from the first subband to one of the ionizing states, if you can turn, please, sorry. Okay, is gonna get lost in the free space. And this means, okay, maybe, okay. This means that we have ionization, which is an irreversible process. But what happens if we manage to couple this system to a cavity? The cavity, sorry, just the remote is not really working. Yes, the cavity will exchange photons with these bound to continuum transitions, and the light matter coupling, we know it would depend on the square root of the number of the electrons involved. This means that if we don't have any electron, because we are not doping the system, we don't have any light matter coupling. And in this case, in terms of optical response, the absorption would be just a continuous band above the ionization threshold due to the all the possible bound to transition to bound to continuum transitions, and one single photon resonance centered at the cavity frequency. But what happens if we dope the system? Sorry, just if you can turn again. Yeah, if we dope the system, we injecting electrons in the quantum well. This means that we are able to achieve a strong light matter coupling. If this happens, we will observe the formation of a novel electronic state, like this one marked here in green. This novel electronic state will have an energy lower than the ionization threshold. This means they will be bound because one electron in this state wouldn't have enough energy to escape from the quantum well, so it would remain localized. In terms of optical response, we will see this state by the formation of a discrete resonance emerging below the ionization threshold, like this one marked here in green. And we can say this is a bound excitonic state because if the electron jumps from the first subband to this novel state, it will remain bound in the quantum well localized. It means that we're actually creating a bound electron-hole pair, not via a mere Coulomb interaction, but by via light matter coupling. So we investigated. Sorry, if you can turn. Sorry. So if we investigated this phenomenon theoretically in this paper published in Optical in 2019, where we calculated the polaritonic energies for such coupled system as a function of the doping level. So as you can see, even when the resonator energy is placed in the continuum, so above the ionization threshold, at some point after a certain value of the doping, we still see the emergence of a discrete polaritonic state. And this polaritonic state coming out from the continuum is actually as a matter component, which corresponds to the electronic transition from the subband to this novel newly created electronic state. In these bottom panels, I plot the electron density of this novel state as a function of the position in the growth axis and as the doping is increasing. As you can see, from the second panel, so after a certain doping level, we observe the ever more localization of the electronic state on the position of the quantum well. So next slide, please. So we did also experimentally observe this phenomenon, and the results are being published in Nature Physics in 2020, and the paper just came out this very month. So if you want to, if you're interested, please check it out. We employed a system like this one sketched here. When a multiple quantum well heterostructure is embedded by this kind of golden microcavity. This kind of microcavity allow us to tune opportunely the cavity energy, and so we can span a reasonably wide range of resonator energy. In panel A, we present the reflectance spectrum as a function of the resonator energy. The green dots represent the resonances for the undoped system, which correspond to the uncoupled photonic resonances, while the blue and the red dots represent the coupled polaritonic resonances. And as you can see from panel B, even when the resonator energy is beyond the ionization threshold, we observe the creation of a discrete polariton mode below the ionization threshold. And this is the result we were looking at. So we can say that this mode comes from a bound to continuum transition coupled to the cavity because of the difference in lifetime of these two modes. From panel C, you can see that the line width of the lower resonance, so the lifetime of this new resonance is basically the lifetime of the resonator, so it's finite. While the upper polariton mode, so the blue dots represent the line width of the upper mode, which is really broadened. This means that this mode is really broadened over a continuum of excitations. So, okay, in conclusion, we say yes, we can use cavity QED effects to engineer opportunely electronic wave functions, and this can make possible to realize tunable semiconductor devices. So these are my co-workers and my collaborators, and I thank them all, and thank you all for the attention.
Okay, thank you. Thank you, Erika, very much. And next speaker is the last speaker of the session. Bo?
Yes, well, thanks everyone, and it's very glad to present here. And thanks for the organizers for organizing the event. So my name is Bo Zhao. I'm working with Professor Senhui Fan at Stanford University. I would like to present our recent result on non-reciprocal thermal radiation from magnetic well sand metals. Next slide, please. So we know that thermal radiation is usually reciprocal, meaning that for a given a thermal emitter, for a given direction, given polarization, and given frequency, the emissivity and absorptivity are usually the same. For example, if we consider the thermal emitter denoted as this plain box with a center T in the middle. So if we consider the emissivity epsilon A in the channel A direction and absorptivity alpha A in the channel A direction, those two values are the same if the emitter is reciprocal. And we can further run a detailed balance analysis and convince us the absorptivity in this channel is equal to 1 minus reflectivity when the light is shined from A then reflected to B, whereas the emissivity is equal to 1 minus the reflectivity when the light is from B to A. So for reciprocal systems, we know that those two reflectivities are the same. Those are directly proven from Maxwell equation. However, for non-reciprocal system, we could expect those two reflectivities to be very different, just like an isolator, and therefore we can get the so-called non-reciprocal thermal radiation. This is also breaking the so-called Kirchhoff's law of thermal radiation. So non-reciprocal thermal radiation not only opens up the freedom for us to control emission and absorption freely, but also has a non-trivial consequence in energy harvesting applications. Here I'm giving you one example in PV cell energy harvesting system. For traditional PV cell systems, the PV cell is reciprocal, meaning that upon receiving sunlight, the PV cell unavoidably is going to back emit some light to the sun. This back emission, however, contains some exergy that we can use to produce electricity. Therefore, it'd be much nicer to completely kill the back emission in this channel and re-guide it to some other direction where we can put another cell. So in order to build non-reciprocal thermal radiator, one way of doing it is use a magnetic field to break the time reversal symmetry. And here I'm showing you a previous work on this topic. And the authors used indium arsenide under a B field and successfully achieved the absorptivity and emissivity being completely different at some direction and some frequency. However, this work is based on, is using an external B field that is on the order of 3 Tesla. For those kind of large magnetic field, it's difficult to achieve practically. That's exactly what we're going to solve in this work. Next, so our approach is based on the so-called magnetic well-set metals. So because of the spontaneous magnetization, the time reversal symmetry in those kind of material systems are inherently breaking. So therefore, the degenerate Dirac cone is going to be split in the K space and forms a pair of well nodes. And more interestingly, the well nodes provides a barrier curvature field for us to access. And the barrier curvature actually acts like a magnetic field in K space, just like the B field in real space, and provides the electron wave packet a so-called anomalous velocity. And this is a component that breaks the time reversal symmetry. And with that, the dielectric function of magnetic well-set metal actually possesses a very similar form as magneto-optical material in a B field. And however, because the anomalous velocity effect is so large, the non-reciprocal effect is on the order of more than 2 to 3 orders of magnitude larger compared to magneto-optical material under a external B field of 1 Tesla. So with those material, next please, we build a grating structure to control the thermal emission. So we see from the band structure shown on the right that the left propagating and the right propagating surface plasma have very different dispersion. And the grating structures outcouple both of them in one direction. And because the different dispersion, they can have a very different property. And with that, next please, we get a emissivity and absorptivity to be completely different at a frequency near 0.56 Fermi level at an angle of 80 degrees. And we can see that this is a completely violation of the Kirchhoff's law of thermal radiation over a relatively broader frequency range. And shown on the right is a counterplot showing that this violation effect actually possesses in also very large angular range. So I hope we convince you that our work opens up the possibility to use magnetic well-set metals to construct practically interested non-reciprocal thermal radiation for heat control, heat flow control, and energy harvesting application. And with that, thank you for your attention.
Thank you. Thank you very much. I think this concludes our hot topics session, but I would like to encourage everyone to go to the Gather Town and find each other and ask questions. I'm sure you have lots of questions. I do, and now we can jump into the Gather Town and talk, and then hopefully we will back to the tutorials again. Thank you, everyone. Bye.